This is section 1416 on the hydrogen deficiency index in terms of the degrees of unsaturation in a molecule. So we're almost done with chapter 14, congratulations. And before we go on to chapter 15, there's one piece of information we need to go over, and that is how to calculate the hydrogen deficiency index. Because even though we can now determine if a molecule has a double bond or what its molecular weight is, or if there are alcohols or bromines or chlorines present, it still doesn't tell us enough about what the structure might be. So we're going to talk about the molecular formula and how that can help us to find out how a molecule is saturated or unsaturated. So in your book, they have 4 drawings here: methane, ethane, propane, and butane. However, what they're showing you here is that each carbon has hydrogens all around it. And if you do if you look at the molecular formula, the number of hydrogens always adds up to the number of carbons times 2 and then plus 2. So in ethane, you have 2 carbons. So 2 times 2 is 4, plus 2 is 6. 1, 2, 3, 4, 5, 6 hydrogens, just like we expect. It's even true for branched compounds. C5H12 can mean pentane, this sec-pentane, or this isopentane. Each of these have the same molecular formula, but as we learned in previous chapters, they could have different structures. And the hydrogen deficiency index is one way for us to know with only the formula if there might be a double bond or triple bond present. Because if there's a pi bond present, then they will have a different degree of saturation, i.e. different number of hydrogens, and so we call them unsaturated because they don't have the maximum number of hydrogens. Alkanes with the maximum number of hydrogens are called saturated because they have the maximum number. If there's a ring, there will also be a reduction in the saturation, even though ring structures are saturated. So we call these, well, I guess they're typically not saturated because, well, no, they are. They still have the maximum number of hydrogens, but a ring structure has 1 degree of unsaturation in the hydrogen deficiency index. So hexene, C6H12, if this was a fully saturated molecule, we would expect it to be C6H14. And for cyclohexane, we would expect C6H14 as well. However, because there's 1 degree of unsaturation, we're missing 2 hydrogens, and now it's C6H12. So before we move on, the formula for the hydrogen deficiency index, or as it's shown here, is shown here from your book. So you take the number of carbons times 2, you add 2, you add the nitrogens, subtract any H's, and subtract any halogens. 1/2 of that number should give you the hydrogen deficiency index, meaning how many pi bonds or rings do we have. If the HDI is 0, that means there are no pi bonds or rings. So let's talk about how we get to some of these numbers. So we already saw that 2 times the carbons plus 2 should always gives us a deficiency index of 0 because, or sorry, plus 2 minus hydrogens, because that should equal 0. 2 times the carbons plus 2 minus the hydrogens. Hydrogens should equal 2 times the carbons plus 2 if the hydrogen deficiency index is 0. So really what we're talking about is how do nitrogens and halogens affect things. So halogens affect the HDI in that you treat them like a hydrogen. So if you have a Cl instead of a H in this case, it has the same HDI, which is the same HDI as ethane, because the chlorine counts just like a hydrogen does. That's why we subtracted here. Oxygens are ignored. And the reason why oxygens are ignored is because they also have a hydrogen attached to them. And so they are just not used because the hydrogen count stays the same. Nitrogens, on the other hand, give an extra hydrogen. So before you subtract the hydrogens, nitrogens provide an extra hydrogen to the molecule. So before you subtract the hydrogens in our HDI calculation, you have to also add the number of nitrogens in the molecule. So like for this example, ethylamine, there are 2 carbons. So that would be 4 plus 2 is 6 plus the number of nitrogens is 7. Do we have any hydrogens? Yes, we have 1, 2, 3, 4, 5, 6, 7 hydrogens. So we had 7 minus 7 is 0. 1/2 of 0 is 0. So we can see that ethylamine is still saturated. But 1 degree of saturation, you see here, can mean 2 different types of structures. 2 degrees of saturation can have different types of structures as well. If you have 2 degrees of saturation, there's probably 2 double bonds, or maybe there's 1 triple bond in the molecule, or maybe there's 2 rings. All of these are constitutional isomers of the same molecular formula, C4H6. So you see that we were able to find out from just the formula what types of structures might be possible. And in doing so, we are giving ourselves a lot more information about the types of double bonds that might be present. And in chapter 15, we're going to be looking at the types of hydrogens that are around these molecules, and the NMR spectroscopy, which is showcased in chapter 15, is so powerful that it can tell us exactly what the structure of whatever isomer it is that we're talking about, of C4H6. So congratulations, you made it through chapter 14, and I'll see you in chapter 15.